Okay, so today what we're really going to do is mostly a recap of just the new mathematical ideas that we have learned, in particular about diffeomorphisms and Lie derivatives. And we'll also discuss a comparison between Lie derivatives and flows, right? And this pushback, pull forward, push forward and pull back, and comparison with this idea of parallel transport and the affine derivative that we had defined earlier. Okay, because it can be a little confusing. Okay, what the differences are between these things, and also we'll try to do some examples. And again, one thing that I'll try to do is stick with sort of, I mean, all these concepts are coordinate free concepts. Okay, you can assign coordinates to a manifold, you can assign coordinates to a metric, but all of the concepts that we've discussed don't depend on any particular choice of coordinate system. Okay, and so I want to emphasize that, and the examples that I give will also emphasize that, because I'm not going to use any coordinate system when doing these examples. I'll just show you pictures, okay, to kind of illustrate what exactly is going on in these different examples. So today there's not really going to be any new content. Okay, it's mainly kind of solidifying the things that we've understood and understanding the distinction between some of the different ideas that we have covered. Okay. So yeah, so let's just start. And also it's intended to be a discussion. So, if you have any doubts or any questions, feel free to bring them up and we'll address them either in the middle or towards the end. If you like, we can discuss some more things. Okay, so let's go back to this kind of handy picture that we have, and it's just good to keep this picture in mind because a lot of the ideas that we're building on essentially build upon this basic idea. Okay, so we started with the very basic idea of a topological space. And within the broad class, and topological spaces were defined by points and neighborhoods of points. Or more specifically, we talked about this idea of open sets of a topological space. So a set plus a collection of open sets defines it. We say it gives a topology to a topological space, and those open sets need to satisfy certain criteria. And we also had mappings between topological spaces, and we said that two topological spaces can be homeomorphic if there are invertible maps between them. And these maps are based on the notion of continuity. Okay, so they take open sets to open sets. So if I have a topological space T with, a topological space X with a topology given by T, which is a collection of open subsets, and I map it to another topological space Y with T prime, okay, then it's a continuous map if open sets of T get mapped to open sets of T prime. Okay, and if this map is invertible, then it's called a homeomorphism. Okay, and this map is based on the notion of continuity, okay, of the map. Now, within the class of topological spaces, we saw a very important class, okay, that is important for us, especially in GR, which are called manifolds. And manifolds are topological spaces which are locally homeomorphic to Rn. Okay, so they are locally homeomorphic to, open sets in Rn. So what that means is that because we know how to do calculus in Rn, we can also do calculus on manifolds. Okay, and so it allows us to define concepts of differentiation. We've seen notions of differentiation, for example, by having a curve. And if you have a smooth function on the manifold, you can define differentiation on the curve by taking derivatives with respect to some vector field x, okay, where x are tangent vectors to the curve. And this allowed us to define a notion of differentiation. And we also have a notion of integration, which we've not yet discussed. Okay, but we've seen that you can, so once I have tangent vectors, I can, or curves, I can define tangent vectors and I get vectors, and we have dual vectors, and you can construct more generally tensors on a manifold. And again, vector fields, smooth dual vector fields, smooth tensors, all of this doesn't rely on the concept of coordinates. Okay, you don't need coordinates. Because manifolds are locally homeomorphic to Rn, you can map them to coordinates which are labeled by the coordinates in Rn, okay, in local patches. But you don't need to do this mapping. Okay, vectors exist independently of such a mapping. Dual vectors exist independently of such a mapping. Tensors exist independently of such a mapping. Okay. then we saw that there's this concept of okay, so now here the new mathematical ideas that we've learned in the last few classes, which is on a general manifold. Okay, you have this idea of diffeomorphisms. That is, you can map now. So a manifold is again a topological space, but now it's locally homeomorphic to Rn. So if I have a manifold M, okay, which includes some coordinate charts, it can be mapped to itself. And if this map is smooth and invertible, okay, then this map is called a diffeomorphism. And we've seen that one class of diffeomorphisms can be generated by flows of a vector field. That is, if I have a manifold M and if I have a vector field X on it, okay, then we have this vector field X generates a flow, and this flow can be thought of as a continuous series of diffeomorphisms, such that in a particular coordinate notation, we have, if I have a point with coordinate X, then under this flow, after flowing by an amount t for a time t, okay, then it gets mapped to the point X prime, which is equal to e raised to tx acting on X. So this gives us a notion of a flow, and again the notion of a flow is actually independent of the coordinate system that you use. We use this more general notation of sigma t x, okay, or sigma tp if you like. Okay, t is the amount of time. It's a one parameter family of diffeomorphisms. For different values of t, you get different diffeomorphisms. And finally, this notion of a flow, we use that to define the idea of a Lie derivative. Okay, and the idea of a Lie derivative was to consider two different vector fields, two different smooth vector fields x and y, and to look at under this flow, we saw that there is a notion of yeah, sorry, I should have mentioned something here. Let me try to insert some more space. So sorry, under a general diffeomorphism, two things can happen. Okay, when you have vector fields, you can push forward vectors and you can pull back dual vectors. Okay, this is actually true for any general map. And since this is a diffeomorphism, that is F and F inverse are both defined, you can in fact push forward and pull back arbitrary rank tensors. Okay, arbitrary types of tensors, you can push forward and pull them back. Okay, so under this map from M to M, what happens is under this map from M to M, so this is M, this is a copy of M, and a point P gets mapped to a point P prime. Okay, so this point P prime here, this point P gets mapped to this point P prime. Okay, so this is F. Okay, and what F does is it takes every single point P on the manifold and maps it to a different point on the manifold. Okay, remember that the space itself, okay, you don't care what coordinates you have, okay, but you do care what the points are. Okay, so the points P and P prime, these are different points. Okay, and the point P gets mapped to some other point P prime. Okay, in this case, P prime is over here. So in the copy, it gets mapped to this P prime. Okay, and this image can occur for every P and P prime. Now what we can do is we have associated, so suppose we have a tensor field of type QR. Okay, so Q vector indices are dual vector type indices. Again, this tensor field exists. If it's a smooth tensor field, it exists at every point on the manifold. So it's defined here, it's defined here, defined everywhere. Okay, and the fact that you can push forward vectors means that if this tensor was a vector type, then you can define the push forward of this tensor, which we denote as F star V. Note that this F star V is the push forward. So if I have a particular vector V, which belongs to the tangent space TPM, okay, I am now getting a vector F star V, which belongs to the tangent space TP prime M, okay, where this P prime is F of P. Okay, and note that this vector, okay, this new vector that I get by pushing forward is not the same vector as if I had a smooth vector field V, then there would have been a V at P, there would have been a V at P prime. Okay, and there would have been vectors V everywhere, okay, on this manifold. But this push forward of this vector is very special, right? It's mapping the vector here to a vector at the image of P, okay, which is P prime. So it's giving me some other vector here. This vector is a vector in TFP of M, which is at TP prime of M. But this vector is not the same as the original vector field evaluated at the point P prime. Okay, because the point P prime, let's say under F, gets mapped to some other point P double prime. Okay, and this vector VP prime will be pushed forward to some other vector F star V, but now evaluated at P double prime. And this F star V, but now evaluated at the point P prime. Okay, so this vector, so the key point is that the push forward of this vector VP, though it belongs to the tangent space TP prime M, and now because this manifold is an identical copy of this manifold, this point P prime is an identical copy of this point P prime, but this push forward vector is not necessarily the same as this vector VP prime. Okay, and similarly, we had this idea of dual vectors and the fact that dual vectors can be pulled back. Okay, a dual vector can be pulled back using F inverse. Okay, so we had this concept of push forwards and pullbacks. Okay, and we can now do this for arbitrary rank tensors using we push forward the vector indices and we pull back the dual vector indices. So you can do this for arbitrary mixed rank tensors, provided you have a diffeomorphism, okay, between M and M. And this allows you to define flows, okay, of any vector field. And now any vector field X, okay, and any vector field X, I can now compare what happens to if I have a tensor T, okay, and it starts at point P. Okay, so I start at a point P and I flow with this vector X. Okay, so X flows to P prime, which is if P has coordinates X, the coordinates of X flow to X plus epsilon X. Okay, where this is the vector field evaluated at X. Okay, so this is the flow of the point. Okay, and in coordinates, it looks like this. Okay, and now what we're saying is if there's a tensor of type QR defined at P, this tensor gets mapped to a tensor of type QR at the point P prime. Okay, under this push forward / pullback. Okay, so you get this tensor of this type. And now what you can do is you can compare. Okay, if I look at my original manifold, the original copy of the manifold, and if I look at the original point P prime, and if I look at the original tensor, okay, the original tensor QR at the point P prime, and I compare it now, okay, with the new tensor at the point P, okay, and I take the difference between these two, T prime QR P minus T QR P prime. I take the difference between these two, divide by epsilon, take the limit epsilon tends to 0. Sorry, this is it. Both of these are tensors at the point P prime, so you can compare them. Okay, that's a really important point. Okay, you can only compare tensors in the same tensor space, which means both of these have to be tensors at the point P prime. The tensors at a different point on the manifold belong to a different tensor space. You cannot compare tensors at some point P with tensors at some point P prime in general, right? You have to, in this case, what we did is we pushed forward / pulled back the tensor from this point P to the point P prime. Only then we could do a comparison with the tensor at the point P prime. Okay, and this defines for us a Lie derivative Lx of this tensor. Okay, at the point P. Okay, so this allowed us to define the notion of Lie derivatives. Okay, it's the flows of tensor fields under some smooth vector field. Okay, yeah, so now this entire idea, okay, of having this diffeomorphism, this flow and this Lie derivative, none of this had anything to do with either having a metric on the space. There was no concept of a metric on the space. Second, we didn't even have the notion of a connection on the space. Okay, manifolds can be assumed to have a connection, but that is an additional structure that you have to put on the manifold. You don't need the existence of a connection to define a diffeomorphism, to define flows associated with the vector field, and to define Lie derivatives. None of that is needed. Okay, so this is kind of like an essential part, or already belongs to the structure. The moment you say you have a manifold, and if you give me a vector field, that automatically starts defining for me a flow or a set of diffeomorphisms. Okay, a set of one parameter diffeomorphisms. And it also allows me to define Lie derivatives of arbitrary tensors. Okay, all of this again is completely coordinate independent. All these concepts exist independent of any coordinate system that I assign to my manifold. Okay. Okay. Now, earlier we had seen that we also have this concept of parallel transport. Okay. So, okay. Sorry. Let me come to this idea of parallel transport later. Okay, so now within the subclass of manifolds, we've seen that we have this a subset of manifolds which are called metric spaces, where you add additional structure to the manifold. You take a manifold, but you pick out a particular 0-2 tensor called the metric tensor. Okay, so this is a manifold with some additional property, okay, which is you picked out a particular 0-2 tensor. So this is called a metric space. Okay, now what we want to see is, given that you had these properties of diffeomorphisms, flows of a vector field, and Lie derivatives, you want to see what happens to the metric under such flows, okay, or under such diffeomorphisms, or what do the Lie derivatives of the metric look like? Okay, so this led us to the concept of isometries. Okay, the concept of isometries. And the concept of isometries was that if you imagine that there is a diffeomorphism, M, which takes you from through some function f, it maps you to M. So this is M. This is a copy of M. This is the point P. Okay, and now this is a point P prime. And now over this entire space, I have a metric G. Okay, which means that at every point there is a tensor of type 0-2. Okay, so this is GP02, this is GP prime 02. And again, these live in different tensor spaces. Okay, so this and this cannot be compared with each other because they live in different tensor spaces. And now what we were saying is that we take diffeomorphisms, okay, from M to M. So the point P gets mapped to the point, some other point P prime here. Okay, so let's call this f of P. And this is the point P again. And now what we want is that we want a special class of diffeomorphisms such that when I take, when I take, so again, let me associate the same metric with this space. Okay, so I will associate the same metric here. So there's GP02 and there's GP prime, okay, which is also of type 02. This is a tensor here. This is a tensor here. But now what I will do, I will use F. Okay, so this point P got mapped to the point P prime. What we will do is you will use F to pull back this 0-2 tensor. So we'll pull back this 0-2 tensor and we will bring it back here. Okay, so when we pull back this 0-2 tensor, we will get the pullback of GP prime, okay, 0-2. Okay, and this tensor in general will not, though it belongs to the tensor space at the point P, will not be the same as the original tensor, okay, G, the metric tensor at this point. Only for a certain class of diffeomorphisms, okay, will this tensor, the pullback tensor, agree with this tensor. Okay, and I will get GP02 is equal to the pullback F star GP prime, but P prime is F of P, okay, 02. So when the pullback tensor matches the original tensor, okay, and if this matching occurs for every P on M, then we say that F is a special diffeomorphism called an isometry. Okay, what does it mean? What does it mean to have an isometry? Well, what it means now is that if so we've seen that there's another way of looking at this, which is instead of pulling back the metric, I could think of pushing forward vectors. Okay, so let's imagine that we have the manifold M with the metric G. And we have two vector fields. So this is X and Y at the point P. And this is the point P prime with the vector fields XP prime. And so let me just draw them in some different direction. XP prime and some YP prime. Okay, this is the copy of the manifold with the point P and the point P prime. And now what I'm doing is I have a metric GP, I have a metric GP prime. I have a copy of the manifold with the same metric, okay, which is the same GP here and the same GP prime here. And now what I'm going to do is instead of pulling back GP prime, what I'm going to do is I'm going to push forward this vector and this vector when I map the point P to the point P prime. So what it's going to do is it's going to give me some vector at P prime, okay, which I call the push forward vector F star XP, and the push forward of this vector, which we call F star YP. Okay. In general, this vector and this vector are not the same as XP prime and YP prime. Okay, these are the push forwards of these two vectors. And now what we're going to do is we're not going to push forward GP. Okay, we could have pushed forward GP using the inverse map, but we're not going to do that. Okay, so we could have pushed forward and we could have gotten F inverse star GP. Okay, if we had done okay, so we could have gotten the metric through sort of this push forward, but instead of doing that, what we'll do is we'll take this metric GP prime, okay, and we'll use it to construct the inner product of these two vectors. That is, we'll take the inner product of F star YP and F star XP. Okay, and the claim is that if F is an isometry, then this should be equal to the inner product of the original XP and YP. Okay, using the, sorry, YP and XP, it doesn't matter because G is symmetric. Okay, but using the metric G at P. Okay, so note that this is an inner product at the point P prime, product at the point P. Okay, F is the mapping which takes me from the point P to the point P prime. And what we're insisting is that for any X and Y, okay, it should be true that this inner product gets preserved. Okay, when I push forward these vectors. And we argued in the last class that this is the same thing as this first line. Is the same thing as instead of pushing forward the vectors, let me pull back the metric. Okay, so let me pull back the metric XP, YP, XP. Okay, or in other words, what we're saying is the pullback of the metric, which is a vector, a tensor at, sorry, this is P prime. Okay, so I'm pulling back the metric from P prime to get a metric at P. And if this is equal to the original metric at P, okay, then I would say, and if this is true for all P belonging to the manifold, then I would say that F is an isometry. Okay, it's a diffeomorphism which preserves the metric. Okay, and the important thing was that when we copied the manifold over, we also copied over the metric. Okay, we copied over the metric. Okay, so we took the manifold with the same metric, and even though the vector fields XP and YP moved to these two new vector fields, okay, the copy of the metric preserved the inner product, okay, of these two. Okay, so you had to move or you had to make this transformation in a very specific way to preserve this inner product. It's not going to be true for all diffeomorphisms that you preserve that inner product. Okay, and which sort of transformations preserve that inner product will depend on what the actual metric is. Okay, we'll do some examples to kind of review this in a second. Okay, but one thing to note is that if I had used the push forward metric, okay, so that is if I'd use F inverse star GP, So suppose I had constructed this inner product, F inverse star GP. So I had used the push forward metric and the push forward vectors. Then what I would get, again by the same argument, is that now I will get F, sorry, the push forward metric will look like this. It's F inverse star, okay, because it's a push forward, so it looks like this. Sorry, yeah, it's actually a pullback using the inverse function. Okay, so it's a pullback using the inverse function, which is why the star is up here. So pullbacks have upper star, push forwards have lower star. And now what we do is we argue that this is the same as, did I make a mistake here? Yes, I think I meant to do F upper star. This is a pullback of G. Sorry, what am I getting wrong? What is the notation that we used? We used lower star for push forward, or we use upper star for push forward? Let me just review the notation. Yeah, lower star is push forward, F upper star is pullback. Okay, so F inverse upper star is the pullback. And here this should have been upper star also. Okay, so now what we do is when we apply this F upper star, okay, so you can argue that this is equivalent to, instead of pushing forward the vectors xp and yp, let me instead take this metric, okay, and let me pull it back, okay, to the metric here, and let me use the original vectors xp and yp and take their inner product. Okay, so let me use the original xp yp and let me pull back, okay, F inverse star GP. And this is just going to give you the original GXY. Okay, so you get nothing interesting if you also push forward the metric and you also push forward the vectors, then obviously very trivially, okay, it will always be true for any map F, okay, that the inner product will be the same. The non-trivial thing about isometries is that you are not pushing forward the vector, the metric G. Okay, you are only pushing forward the vectors xp and yp, but you're using the actual metric gp prime. Okay, you're using the metric gp prime, and you're only pushing forward these vectors. And when you push forward these vectors and take the inner product, okay, with this gp prime, you get exactly the same thing as you would have got if you're taken gp on xp and yp. Okay, so that is a highly non-trivial statement, and it only works for some particular diffeomorphisms. Diffeomorphisms which kind of transform you from points P to P prime along some symmetry directions of the metric. Okay, which preserve directions where, you know, when I go from P to P prime, I'm preserving the metric. Okay, so that's what's special about these diffeomorphisms, and that's they're called isometries because they preserve the metric. Okay, so iso, same, metry is metric. Is this idea clear?
Yes, sir.
Yes.
Okay. Yeah, any questions?
Yes, sir. So, just out of curiosity, are there so first we'd like define a metric, and then we have this certain class of diffeomorphisms that are isometries. What about metrics that have this that are preserved under all diffeomorphisms? Is that something trivial, or
Metrics which are preserved under all diffeomorphisms, that is actually impossible. Okay, for a manifold of dimension n, okay, Yeah, actually, it's impossible to preserve the metric under all diffeomorphisms. Okay. Let me give you a simple example. Okay, so let's take Minkowski space. Okay, so we take Rn, or let's just take Rn with a Euclidean metric delta. Okay, so we know that, or let's take for example R3. Okay, so this space has only the following diffeomorphisms, which are isometries. Okay, I can only do translations or rotations or a combination of translations and rotations. And I can also do these discrete transformations of reflections. Okay, but that's it. Okay, so these transformations in terms of coordinates, they look like, for example, translations look like, or sorry, rotations look like this by a rotation matrix where R is orthogonal. Okay, and if it's a pure rotation, then determinant of R is 1. If it's a reflection, then determinant of R can be -1. And in R3, okay, and a translation would be I add a column vector T to it. Okay, so this is the set of all possible diffeomorphisms, which are isometries, that is, they preserve the metric. But now if I do some kind of nonlinear transformation, okay, so like let's say x goes to x cubed. Okay, this is a diffeomorphism which will not preserve the metric. It's actually impossible to have all diffeomorphisms preserve the metric because the metric defines a structure in the manifold. Okay, and now every point is distinct from every other point. Okay, because each point has a particular metric associated with it. And it's not possible to make transformations on this manifold anymore in such a way that the metric is preserved under all diffeomorphisms.
Okay, sir.
Okay, and in general, if I talk about the continuous diffeomorphisms, okay, there are, so this is the thing we'll talk about next. Okay, we'll talk about isometries, which are continuous isometries. Okay, so we've discussed how diffeomorphisms, or at least continuous diffeomorphisms, can be thought of as one parameter flows associated with some vector field. Okay, so similarly, these isometries are also diffeomorphisms, and they can be thought of as one parameter flows generated by a particular class of vector fields, and these vector fields are called killing vector fields. Okay, so these killing vector fields are such that if I have a manifold M and its copy, this is the metric G on this manifold, and there is a vector field X, okay, on this manifold. And this vector field X generates a one parameter family of flows, okay, which means there is a function f which maps me to a copy of this manifold, okay, with metric G, and it takes a point P, okay, with coordinates X, and it maps that point P to a point f of P, which has coordinates e raised to tx x. Okay, this is the point P prime or f of P. Okay, so this is the mapping, okay, from this point to this point, and it's continuous, and this sorry, it's a diffeomorphism. Okay, it has an inverse as well. Okay, and now the point is that this f is, if we want this f to be an isometry, that is, we want it to preserve the metric. Okay, which means that the pullback. So if I have the metric G of fp, okay, so if this point was f of p, and this metric here was G of fp. When I pull back this metric back to this point, I should get back the original G of p. If I don't, then this map f is not an isometry. If I do, then this map f is an isometry. Okay, again, if this pullback gives me back the original G of p, so that is if G of fp, when I pull it back by f star, if it gives me back the original GP, then this is an isometry. Okay, if this happens for every p belonging to M, then then this f is an isometry. Okay, and this f is a one parameter family of flows, which means for every t this is an isometry. Okay, so for every t this is an isometry, and then we say that there is a particular generator of these flows called which is the vector field x, and we say that x is a killing vector field. Okay, because it generates this family of diffeomorphisms which are isometries. Generates flows or diffeomorphisms which are isometries. Yeah, and in particular, what this means is that when I generate a flow with x, okay, so G transforms, and what we're saying is that G basically is not changing under this flow, which means that we're saying that the Lie derivative of G is 0. Okay, this defines a killing vector field. So vector fields x for which this Lie derivative is 0, these are killing vector fields. Okay, that is when I transform P by going along this flow to the point P prime. Okay, so in the copy manifold, I'm at the point P prime. And now I take the tensor here, I pull it back to the point P and compare with the original tensor at the point P, and I take the difference between those two. So that is the Lie derivative. Okay, where this x is the direction in which I am causing a displacement. Okay, or generating my flow. So when I compare the pullback of G, so G of FP, the pullback minus the original G divided by epsilon, where epsilon is the amount that we flowed. Okay, limit epsilon tending to 0. This is the Lie derivative of G. If this is 0, okay, then we say that the metric has not changed under the flow. So this defines a particular set of directions on the manifold. Okay, at each point, you're telling me what direction I need to flow, okay, in order to preserve the metric. Okay, so when we think about, let's say, again, Euclidean space R3 with metric delta, and we're saying that there's a metric here, there's a metric here, there's a metric here. Again, remember that this metric is a coordinate independent notion. Okay, the metric is a coordinate independent motion. I don't care whether you use spherical coordinates or any other coordinates, right? The metric just gives me a way to take dot products of vectors. So if I have any two vectors here, it'll tell me how to take the dot product of these two vectors. Okay, these vectors live in the tangent space, so they could be, you could think of them as electric fields, you could think of them as displacement vectors, it doesn't matter. Okay, so any two vectors, okay, I can take the dot product of these vectors, and the metric just gives me a prescription for how to take that dot product. Okay, and so it gives me a way to calculate angles between vectors or the norm of a vector or something like that. And now what we're saying is that when we say that there are special directions or special flows of points from P to P prime, which preserve the metric. Okay, so for example, we're saying that translations preserve the metric. So which means that if I move from this point to this point, okay, and I see how these vectors get pushed forward, okay, the dot product of these two vectors will remain the same. Okay, under that push forward. And this would be true for all points which are translated to the right. Okay, similarly, this would also be true for rotations. Okay, that in the case of rotations, if I have a vector x and a vector y under a rotation, okay, this point x gets rotated, the vectors themselves also get rotated. So you think of it like this. So this is at an angle theta. Okay, this vector x also, you can think of it as rotated by theta. although I'll discuss this in detail. When we say rotated by theta, rotated relative to what? Okay, so this is the tricky point, rotated relative to what? Okay, and really we should only think of this as the push forward of x. Okay, but we'll try to get an intuition for the push forward of x. And this relative rotation of the push forward, okay, it only makes sense in a flat space. Okay, we'll see why that is, but I told you the idea last time, which is in flat space, parallel transport always is basically a benchmark. Okay, so I can parallelly transport this x to this x here, which we call x parallel, xp parallel. And it doesn't matter what path I take to get here, all paths will give me the same vector after parallel transport because my space has no curvature. If I have curvature in my space, then different paths will give me a different version of a parallelly transported x. So if I don't have such a notion of a universally parallelly transported x, then there is no way to compare this vector x, which is the push forward. Okay, this is the push forward of the original x. There is no way to compare this with any other vector here. Okay, so we're not. So this comparison of saying that this x is rotated, this only works in flat space. Okay. In general, the important point is that the dot product of this x and y, that is preserved under rotations. Okay, this dot product of x and y is preserved under rotation. So rotations or rotational killing vector fields give you killing vectors on R3. Okay. Yeah, sorry. There's one more important point. Which is kind of a nice picture to understand. So we said, supposing you have a manifold M, okay, and let's imagine that there are two vector fields, x and y. Okay, so at every point I have x and y. This is at P, this is at P prime. Okay, these are vectors at P and P prime. And now what we say is, let's consider two different flows. Okay, one by x. First we'll flow along x by an amount epsilon. Then we'll flow by an amount delta along y. And then we can do the same thing in reverse. We flow first along y, and then we flow along x. Okay, and we've seen before that these two flows can be incompatible with each other. Okay, that is, you may not end up at the same point after doing these operations in different directions. So the incompatibility of these flows is measured by something called the Lie bracket. Okay, so if I take the difference between which point I end up at, okay, so if I look at the point x prime and the point x double prime, the difference between the coordinates of x prime and x double prime is roughly related to the Lie bracket of x and y, and it's proportional to this epsilon delta. Okay, so this gives me a vector, this xy Lie bracket, okay, which is the same as the Lie derivative of y with respect to x. It measures the incompatibility or the incommensurateness of these two flows. And it tells me that there's an extra displacement that I must cover. This extra displacement is epsilon delta xy. And when I cover this extra displacement, I will get from this point to this point. Okay. Now let's understand this in the context of killing vectors. Okay. So let's suppose x and y are killing vector fields. Okay, so x and y are killing vector fields. So what that means is that when I flow from here to here, I'm preserving the metric. Okay, that is, if I pull back the metric from this point to the original point, then I would get back the original metric. Similarly, if the flow along x is also an isometry, that means that when I pull back the metric from here, I would get back the original metric. Okay, and similarly, if I go from here to here, okay, this is an isometry, so if I pull back the metric, I would get the original metric. If I go from here to here and I find the metric at this point, and now I pull that back here, I would get back the original metric. Okay. Sorry, let me just backtrack. So just along y, if I flow and I pull back, then I'll get back the original metric. Just along x, if I flow and I pull back, then I'll get the original metric. Okay. Now what we're saying is that if I go here and I pull back, I get the original metric. If I go this way and I pull back, I get the original metric, which must mean that if I go from here to here, that is along this magenta line, and I pull back, then I should get back the original metric. That is, I should, if starting from here, if I go back along this magenta line and I pull back the metric, I should get back the original metric. Which means that this displacement vector, which takes me from this point to this point, which is proportional to the Lie bracket or the Lie derivative, that should also be uh, a killing vector. Okay, that should also be a killing vector field. Okay, which is why the killing vector field, the space of killing vector fields is closed under the Lie bracket. So the Lie bracket of any two killing vector fields gives me back a third killing vector field. Okay, so among the set of flows, okay, so if I have any vector field on the manifold, it generates a flow. Okay, there are special subset of these. So this is the set of all flows, set of all vector fields. And this generates smooth diffeomorphisms, okay, smooth one parameter diffeomorphisms. And now among these, okay, we can pick out a subset, okay, subset K, such that the commutator of any two of these within the subset, so the Lie bracket of any two within the subset, gives me a third element of this subset. Okay, these are special flows. These generate special flows. Okay, which are isometries. Okay, and it's also now we've seen pictorially why it must be true that the Lie bracket of any two of these must give you back a third, another isometry. Okay, something else that generates a special flow, which is also an isometry. Okay, any questions at this point?
Sir, can you explain this pictorial thing once more?
Yeah. So when we start, okay, so let me just do it again. So let's start at the point P. Okay, and this is a flow generated along X by an amount epsilon, and I go to some point P prime. Then there's a flow by an amount delta along Y. Okay, and then I go to some point P double prime. And then there's a flow by an amount delta along Y. Okay, and I go to some P triple prime. And then there's a flow along X by an amount epsilon, and I go to some point P 4 prime. Okay, and the difference between these two we've seen before is epsilon delta xy. Okay, maybe up to minus sign. Let's not worry about the minus sign. Okay, so now what we're saying is that this x and y are killing vector fields. Okay, so we're looking at the special case where x and y are killing vector fields. Okay, in this case, what does it mean? It means first let me take the original metric at all these points. Okay, so this is a metric defined at all these points. Okay, and now what we'll do is, since X is an isometry, since X generates an isometry, what that means is if we go along the flow and then we pull back this metric back here, then the pullback of this metric, okay, along this flow should give me back the original metric. Okay, because X is an isometry. Okay, or X generates an isometry. Similarly, if I flow along Y and I pull back this, okay, then I should get back the original metric because Y also generates an isometry. Okay, and similarly, if I flow from here to here, okay, and I pull back first from here to here, then I should get back the metric here. Okay, and then if I pull back again, then I should get back the metric here. Okay, so basically I can pull this back along this path and I can pull this back along this path and I should get back the original metric because X and Y are isometries. Okay, but now it must also be true, okay, that therefore when I pull back, let's say from here to here, okay, from here to here, that I get back, go from this metric to this metric, okay, which can further be pulled back here, okay, or you think about it as the closed path, okay, isometry, okay. So it must be true that as I go along this closed path, okay, that automatically that it must be an isometry, right? Because this is just the this entire thing is mapping P to P, so it's just the unit or the identity map, okay. So the identity map is obviously an isometry. Okay, so this closed path map is an isometry, which means that this extra displacement, which I must cover from P quadruple prime to P double prime, this must also be generated by an isometry. And this extra displacement is proportional to the Lie bracket of xy. Okay, so therefore the Lie bracket of xy must also generate an isometry.
Yes, sir, I got it.
Okay. Yeah, so the fact that this Lie algebra of killing vectors closes gives you the fact that there is a killing algebra. Okay, that is any two killing vectors up to are equal to some third killing vector. Okay, the Lie bracket of those two is some third killing vector. Okay, and you can get a basis of killing vector fields. Okay, you can get a basis of killing vector fields, and let's in n dimensions for an n-dimensional manifold. Okay, the basis of killing vector fields is of dimension n into n plus 1 by 2. Okay, we've seen that, for example, in the case of Rn, okay, you have nc2 rotations plus n translations. Okay, and this together gives you n into n plus 1 by 2 killing vector fields. Okay, and remember that linear combinations of a translation and a rotation, or linear combinations of translations, those are also killing vector fields. What we're doing is finding a basis, okay, of those killing vector fields. And in n dimensions, this is the maximum number. Okay, n into n plus 1 by 2 is the maximum number of killing vector fields that you can have of the basis. Okay. Okay, but if I take all possible vector spaces on the manifold, that vector space of all, sorry, the vector space of all smooth vector fields, that is an infinite dimensional vector space. Okay, I can have any number of vector fields, right? So the space of killing vector fields is a much more restricted set. Okay, and again, one thing that I'll emphasize, okay, is that flows of a vector field do not give you all possible diffeomorphisms. For example, discrete diffeomorphisms like a reflection, that can never be generated by a continuous flow. Okay, this one parameter of flows. So these only give you continuous diffeomorphisms. Okay, and similarly, killing vector fields will only give you continuous isometries of the metric. You can have discrete isometries of the metric, which you cannot find from killing vector fields. Okay. Okay, now let's go back to some of the things that we had learned earlier. Okay, so now let's look at the concept of a manifold again without a metric. Okay, so we've seen that you can have diffeomorphisms, flows of vector fields, and Lie derivatives, but we had seen earlier that I can impose additional structure on a manifold. What is that additional structure? That additional structure is I can define parallel transport, but I have to tell you something more on the manifold. Okay, a manifold by itself doesn't give you a notion of parallel transport. I have to give you something called an affine connection, or in a coordinate dependent way, I can give you this gamma, these connection coefficients. Okay, and this will tell me how to parallelly transport, but this parallel transport is curve dependent. So if I give you a curve and I give you the connection on the manifold, you can tell me how to take a vector from here to some other point here by parallelly transporting it along the curve. Okay, and this connection can have torsion, and this connection can have curvature. Okay, these are some various properties that we've seen. And once we have a connection, we've seen that there's special classes of curves on the manifold, which are straight curves. Okay, where if I take this curve and I look at the tangent vectors to this curve, then the tangent vectors are such that the tangent vectors are not changing as they're parallelly transported along the curve. Okay, which means that I can. Okay, so first let me define again what is the concept of parallel transport. Let me just remind you this idea of parallel transport. Okay, so here's a manifold M. Again, no need for a metric. Okay, but I do need to specify a connection. Okay, either through in a coordinate dependent way through gamma, or in a coordinate independent way by specifying something called an affine connection. Okay, which is a derivative operator. So if I have a point P, okay, and I have a vector M, and I have a curve passing through this. Sorry, and this is a vector V, let's say, and I want to parallelly transport this V along this curve. Okay, so I want to get this V parallelly transported over here. Then the way I would do this, okay, in a coordinate dependent way, if this is X and I displace to X plus delta X, okay, where this is the coordinates, then what we argued is that V parallel, okay, the muth component of V parallel would be equal to the original V at the point P. Okay, so this belongs to the tangent space T at P prime. FM, and I'm comparing it with the original vector which belongs to TPM. Okay, and what we have argued is that this will be equal to the original vector. The components will be the same as the original vector, but there will be also some linear combinations, okay, which depend on V, sigma, and delta X rho. Okay, so in other words, I'll take a linear superposition of the components of the original V. Okay, and the difference between these two vectors for small delta X will just be proportional to delta X. Okay, so this is how we argued that you will have this idea of parallel transport. And now what we can do is we can compare. So if I have a smooth vector field V, then I have V at the point P and I have V at the point P prime. And I can compare the parallelly transported V with the V at P prime, take the difference between the two. So we'll take V parallel minus V at P prime. Okay, now these both belong to the same tangent vector space, which is at this point. I can take the difference between the two, divide by epsilon, and this defines for me the derivative along this direction delta X. Okay, along the direction delta X, let's say X nu. Okay, so this would be something like this. Of V is equal to this, and the limit epsilon tends to 0. So this defined for me a notion of an affine connection. Okay, and in general, if I want to differentiate along some vector field X, okay, then we defined we required that it's linear in the components of that vector field X. So this was defined to be X nu partial mu V partial nu V mu plus gamma mu nu rho v rho. Okay, and this entire thing is a vector. Okay, it's the difference between the vector, the original vector field at the point P prime and the parallelly transported vector at the point P prime. So this is in components. This is epsilon mu, E mu, where these are basis vectors. Okay, so this is the derivative. This is the affine connection, and this allowed us to define parallel transport. Okay, so the key point is either I need to specify a prescription for giving me these affine derivatives, or in a coordinate dependent way, I need to specify these connection coefficients. Okay, and so parallel transport required me to define these. And now we saw that if you have curves for which the tangent vectors are parallelly transported, that is, if I take a tangent vector along this curve, T, and I compare it with after parallelly transporting it, then I would find that this derivative is zero. This affine connection is zero. That is, if I take the tangent vector here, parallelly transport it to this point, compare it with the tangent vector this point, take the difference between those two, that difference is zero. So the tangent vector is always transported parallel to itself. Okay, these are the straightest possible curves that you can have on a manifold. Okay, so these define for us what are called geodesics. Okay, so geodesics again don't require the concept of a metric. They give us the straightest possible lines, okay, on a manifold. And the only thing that they require is this additional structure, which is the notion of parallel transport or some kind of affine connection or connection coefficients. Okay, so this was just for points which are, on manifolds. Okay, but now what you can do is you can look at what happens to this concept when you introduce a metric. Okay, when you introduce a metric on the space. When you introduce a metric on the space, there is a unique metric compatible coefficient, metric compatible connection, which is torsion free. Okay, so among the many possible choices that you can have for a connection, okay, one particular connection gets picked out for you. Okay, that is the unique metric compatible torsion free connection, which is unique. Okay, and this you have an idea of a curvature. A curvature can be defined here as well. Okay, but here the curvature we've seen has some more symmetries, okay, including these Bianchi symmetries, okay, or Bianchi identities. So there are some extra symmetries that you get, okay, in the case of this unique connection, metric compatible connection. And now the geodesics, which are associated with this particular connection, they become even more special. In addition to being straight lines, they also extremize the arc length. So they become the shortest or longest possible line connecting 2 points on the manifold. Okay. So if 2 points pass, if a geodesic passes through 2 points, then the geodesic maximizes the distance, okay, between these 2 points. Where now I have a concept of distance because I have a metric. Okay, so essentially the important takeaway, okay, in this, we'll do some examples to see the difference between Lie derivatives and affine connection. And but the important takeaway is that all of this, diffeomorphisms, flows of vector fields, and Lie derivatives, this did not require you to define a connection on the manifold. Okay, nowhere were you required to define a connection on the manifold. Isometries are specific diffeomorphisms that get picked out by the choice of the metric. Okay, killing vector fields are again specific vector fields that generate those isometries, or at least generate the continuous isometries. And whereas the parallel transport and this metric compatible connection, okay, these are extra structure that is imposed on the manifold. This extra structure is unique when you specify a metric. Okay, there is a unique extra structure that gets picked out for you. But yet this structure is distinct from the structure of these diffeomorphisms or the Lie derivatives associated with these killing vector fields. Okay. Okay, and the other thing is that this notion of parallel transport is path dependent. Okay, in general, this is path dependent. Okay, so parallel transport is path dependent. So you have to specify the curve along which you're parallelly transporting in general. Okay, so it depends on the path, and it also depends on this additional structure, which is the connection that you choose. Okay, on your manifold, which is not originally associated with the manifold. It's something additional that you have to supply to the manifold. Once you have a metric, there's a unique supply of a particular metric compatible connection called the Christoffel symbol. Okay, is this clear? We'll do some examples next, but any questions at this point?
Hello,
Yeah.
sir. This parallel transport is path dependent, but the connection, I mean, the covariant derivative we have defined, this turns out to be unique, or this is also depends on path, because we compare two vector. One is the parallel transported, and other is the value of that vector field at that point. So, if it depends on path, then the value of the parallel transported one should change for the different path, and we will get uh, mm, different covariant derivative.
Sorry, you're asking about this?
Yes, sir. I mean, uh, so this depends on the parallel transport. We compare two vector. One is parallelly transported, and other is I mean the vector field at that point. So if the parallelly transported vector depends on the path, then this covariant derivative also should depend on path. But we say this is a tensor, and
No, so okay, yeah. So this is okay. So to be clear, this is sort of this is a comparison of along an infinitesimal path. Okay, so along an infinitesimal path by yeah, this is a good point. So let's look at this. Okay, so what we're saying is let's take the point X. And what we are going to do is we are going to take which point? We're going to take the point at X plus delta X along the V direction. So V generates for us a displacement. So delta X nu will be equal to V nu. This is still a coordinate dependent way of looking at it, so okay, and then we take W here. This is W at X. This is W at X plus delta X. And this is Wx parallelly transported to this point. Okay. So now we're comparing Wx parallelly transported minus W at X plus delta X. And we're claiming that the difference between these two, okay, is so Wx parallelly transported minus is, so this Wx parallelly transported is, sorry, I think it's the other way around. We want Wx plus delta X minus Wx parallel transported divided by epsilon. divided by delta x nu. Yeah, so this we define to be the derivative along the new direction, okay, of W. And if you have a vector field V, then we just demand linearity of this derivative. That is, we say that del VW is just this. Okay, so this is an extra demand that we make. And in fact, this is the key demand. Okay, because this property is not satisfied by the Lie derivative. Okay, the linearity in this V that we differentiate with respect to, that is the key point. Okay, so now when we evaluate this quantity, or at least in a coordinate dependent way, what we're saying is W of x plus delta x minus W of x parallel. W of x parallel is W at x minus this connection. Okay, so let me put in this is now in components, this E mu. There's gamma mu nu rho delta x nu what more do we want? W rho. Okay, this times V nu divided by delta x nu. So this difference divided by delta x nu is partial W mu nu along the new direction. And this extra part is gamma mu nu rho W rho V nu K E mu. Sorry, the whole thing times V nu. Okay, so the key point was this linearity in V. So when you say path dependent, okay, path dependent means we're specifying the tangent vector V, okay, along which we're taking the derivative. Okay, so we're going along a different path, we're changing the derivative, okay. And also we can be traversing the path at different rates, okay, which would scale this vector by some amount. But what we're demanding is that this vector is such that it scales directly in proportion to the magnitude of this V or the components of this V. Okay, so the path dependence comes from this linearity in V.
Yes, sir. Got it.
Sir, like the path dependence actually comes because of that vector v, right? Because that vector v is the tangent vector along the path which that we are taking.
Yes.
Yeah. So like if we take a different path, then actually that the point that will end up at will be different. Like because del x nu will be then some v prime nu. Like if
No, sorry. So this was a mistake. Okay, so this is only giving me a direction, and I take an infinitesimal displacement, but I don't care actually how much I displace by. Okay. Um. Okay. Sorry.
Yeah. So like if I move very like by a very small amount, then like if I take two different paths, I will end up at two different points.
No, sorry. To be clear, you're not actually displacing along V. So in the sense of the diffeomorphism that we're doing in V, right, where x goes to x plus epsilon V, that is not what we're doing here. Okay, this is not a diffeomorphism in that sense, right? This is a motion along a curve. Okay, and Yeah, what is this point that we're going to along? This is a point along the curve. So what are the coordinates of this point, which is infinitesimally nearby along this curve?
Oh, yes. The only constraint on the curve is that it passes through x. And
It passes through x and has tangent vector v.
v, I mean the v for a particular path, but for some other path it will be some v primed.
It'll be some v prime.
Then how can we end up at the same point, like x plus del x?
Yeah, no, that's why it's proportional to v nu. So what are we doing? Are we actually displacing along this direction? So I want to say we're not displacing along this direction.
Sir, and also from like different paths we get the different tangent vectors at the point x.
From the different paths, we get different tangent vectors at the point x. Yes. Yeah, so this is along the curve, right?
Yes.
So maybe the displacement is this.
Yes, here actually this v also generates the displacement.
This v does generate the displacement, and so I must be dividing by this epsilon, really. So I am dividing by, so this delta x nu.
So this term is a flow generated by the field vector field v mu, no? X mu plus epsilon v mu.
Yeah, if I do this, it looks like a flow. At this point, at least, it's a flow generated by v.
So can you think it in another way, like first we define 2 points and then to find the curve which maximally transport it maximally parallelly.
What do you mean maximally?
I mean the maximally means different curves will parallelly transport in by different amount, but the maximum parallel transport, the orient component of vector should remain the same.
I don't understand that. Can you say that again?
Uh, what I want to say that first we define two nearby points, like because we want to find derivative, and look for the curve which along which that vector field get maximally parallel transport. Maximally means in the sense like because two different curve uh, will not transport the vector equally parallel. So I don't
Yeah,
know.
I mean, if I go this way or I go this way, I'll get a different vector if I go here. And I
E-
cannot even compare these vectors, right?
Even for the same endpoint, if I take two different paths, then amount.
Even for two different paths, it's true.
So can we do? Can we? First fix the endpoint and then find a path for which the parallel transportation will be maximum.
Will be maximum. What do you mean by maximum?
Component will change.
I don't
The
think that's the right way to look at it because this is a component independent definition. So, I mean, there's no maximization over components. I mean, because if I change coordinates, then what is a component changes, right?
okay. Okay.
So, yeah, but this is one curve, this is a different curve, and this is a different tangent vector v, and this is a different tangent vector v double prime. Yeah, so the tangent vector only gives me infinitesimal displacements, right? And there's a unique sort of infinitesimal displacement. So, I mean, this point that I'm reaching, I can only reach it by one particular tangent vector. I can't reach it by two different tangent vectors. So it looks like it must be coming from this kind of infinitesimal displacement. Okay, that is the point that I'm actually talking about here. But the slightly strange thing is that, yeah, it's the linearity of V is really the key point here in the components of V. Okay, maybe I have to, sorry, maybe you guys can also think about this. Okay, is this point is certainly, obtained by displacement, okay, of this form. And it's an epsilon variation, but how do we rephrase it in terms of the difference between this point, the vector W at this point, okay, and the parallelly transported version of W at this point? Okay, I mean, certainly you can write it like this, but how do we write it in terms of the this quantity? So maybe you can think about that. All right, but let me just finish what the rest of this discussion, and we'll think about this after that. Okay, so and basically this is really the key point which makes an affine connection different from a Lie derivative, because normally when I take two vector fields and I take the Lie derivative, okay, this so if I take L fxy, this is not equal to f Lxy. But for for an affine connection, this linearity of this derivative is true. Okay, and this is the key thing that distinguishes the Lie derivative from the affine connection. All right, and yeah, and pretty much, one of the main things is that you need this kind of connection coefficients if you want to define linearity, okay, of this derivative. Okay, which you don't need for the case of Lie derivatives, which are defined, via diffeomorphisms. Okay, so let's just do some examples, okay, to make this completely clear. Okay, what is the difference between a Lie derivative and what is the difference between this affine connection? So we'll do the two examples. So one is on R2 with the metric delta. Okay, and the other example that we'll do is on a two sphere with the standard inherited metric from R3. Okay, that is ds square is sine square theta d phi square plus d theta square, and this one is in the standard Euclidean coordinates is dx square plus dy square. Okay, so if I just look at R2 with delta, okay, there's so this is R2, there's delta, and now if I look at, let's say, the metric, okay, so the metric is this, or in this particular coordinate system, G is 1, 1. Okay, but remember that the metric is defined independent of any coordinate system. It's a tensor. Okay, it's a dual tensor, and that tensor exists no matter what coordinate system you use. At every point on the manifold, there is a particular tensor, okay, that you're using. Okay, and this is expressed in a particular coordinate system. There's a transformation rule to go to another coordinate system, but the tensor exists independent of any coordinate systems that you assign to the manifold. Okay, and it's a way to measure, it's a way to take dot products of vectors. So now if you give me two vectors, okay, so for example, if you give me this vector v, which is vx, and w, which is in components, then I can take the dot product of these two, okay, which would be, it would just be this. Okay, which is just a complex, I mean, a real number which is defined differently at different points on this plane. Okay, so the vector field V can be anything. It can be any vectors, and the vector field W can be anything. Okay, as long as it's smooth. And this prescription is giving me, it's taking two vector fields, taking the dot product, and so it's giving me a real number, which is the dot product at every point on the manifold. Okay. Or in other words, G is a map from two, it takes in two vectors as input and gives me a function on the a smooth function on the manifold. Okay. Okay. So now what we'll do is we'll look at so we look at first thing we'll look at is the killing vector fields. Okay, so we've seen on R2 there are three bases of killing vector fields. The basis killing vector fields are translations in the x direction, which are basically the vector field partial x, okay, which looks like this. The vector field partial y, which looks like this. And the vector field x partial y minus y partial x, okay, which looks like this. Okay, maybe I'm getting the overall sign wrong, but it doesn't matter. Okay, it looks like it looks like it generates a rotational flow. Okay, so these are the basis of your killing vector fields. This is translation along the x direction, translation along the y direction, and this is a rotation along the, well, would be z direction. There's no real z direction. So we'll really think of it as a rotation in the xy plane. Okay, in general, in n dimensions, you should think of rotations as rotations in a plane. Okay, okay, so now I have these rotations in a plane. Okay, and now these are my three killing vectors. Killing vector fields. A general killing vector field is some an arbitrary linear combination of these. Okay, so an arbitrary linear combination with constant coefficients C1 Tx plus C2 Ty. These are constants. Okay, I cannot change them at different points on the manifold. Plus C3 Rxy. This is a general killing vector field. The algebra of these killing vector fields is closed. Okay, so this is 0. Rxy Tx is something like Ty, maybe up to a minus sign. Rxy Ty is minus Tx. Okay. So this is what the algebra of these killing vector fields looks like. And obviously any killing vector Lie bracket with itself is 0. Okay. Yeah. Now what you can do is you can look at yeah, so what this means is that the Lie bracket also of Tx, Ty is 0. So Lie derivative of Tx is equal to Ty. Okay, so what this means is if I, so what does Rxy do? Rxy generates a diffeomorphism, okay, which is a flow like this, okay, it generates this rotational flow. And now if I flow in epsilon amount, okay, I'm basically rotating my R2. Okay, I'm kind of rotating my R2 like this. And what we're saying now is that under this rotation, okay, the Tx vector field, okay, which was this one, under this rotation, Tx changes, okay, it changes slightly, which means that after we make the rotation, okay, so this vector field, so the Tx vector field here was like this. After we flow to this point, let's say, okay, the Tx vector field is now slightly like this. Okay, it has slightly rotated. So this is my new Tx. And this Lie derivative, what the Lie derivative is doing is it's taking the Tx after my rotation, okay, after my diffeomorphism, minus the original Tx at the point P. And this is the, the original Tx at this point. Okay, the original Tx at this point also looked like this. Okay, this was the original because all the Tx vectors were the same. Okay, they were just these. We're taking the original Tx vector at this point and comparing it with the push forward of this Tx vector after moving it here. Okay, and after we push forward, okay, the difference between these two is a vector like this. Okay, and the difference between these two vectors is therefore this way. Okay, it's a vector which it's basically equal to ty. Okay, it turns out to be exactly equal to ty. Okay, so basically the difference between the Lie derivative of tx is equal to ty, and this is true not just at this point. It's going to be true everywhere. Okay, on the manifold. So in general, as I move along this flow, of course, I don't have to rotate just tx. I can rotate any vector field, okay, by this flow. Okay, what is going to happen is along this rotational flow, if I imagine the vectors, okay, if I imagine any vector here, under this flow, what happens to it is that this vector, this point gets rotated to the point P prime. I'm rotating about this origin, but also I can think of this vector itself as being rotated. Okay, by an angle theta. Okay. And that's exactly what you would expect for any actual rotation. Okay, for any actual rotation, I mean, if you imagine the sheet of paper and you just rotate it, right? If I just rotate my entire sheet of paper and move this point to this point, then this vector would also have rotated by an angle theta. Okay, and it would be like this. Okay, it would not obviously be pointing this way once I rotate the entire sheet of paper. Okay, it would now be pointing an angle theta this way. Okay, now an important point is that when I said it's rotated an angle theta, what am I comparing it with? Okay, what am I really comparing it with when I say it's rotated by an angle theta? What I really want to do is compare it with the original vector here and say it's rotated by an angle theta. Okay, but I can't really make that comparison in general because this tangent space is not the same as this tangent space. Okay, so there is no way to really, but intuitively we know that this makes sense. Okay, that we've rotated the sheet of paper and we want to compare this with this and we say that this is rotated by an angle theta. Okay, but what is the real comparison we're doing? The real comparison we're doing is that we're also parallelly transporting this. Okay, we're parallelly transporting this from here to here. But parallel transport is path dependent in general. Okay, parallel transport is path dependent. In general. And what that means is that in general, the parallel transport on a general manifold, there is no unique way of specifying what the parallelly transported version of this vector is. Okay. However, in a spacetime or on a manifold which is flat, okay, that is has no curvature, and that is true for this R2 delta. Okay, there is no curvature. Then all paths, no matter which path I take to get here, okay, all paths will give me the same reference vector here. Okay, they'll give me the same parallelly transported vector. Okay, so therefore, there is a unique comparison that I can make between the vector x, this vector x after a diffeomorphism and this vector x after parallel transport. Okay, because parallel transport is path independent, I can make this comparison. Okay, and say that the vector x after diffeomorphism is rotated by an angle theta. Okay. Now any two vectors, okay, so if I take, so this was the vector x, okay, which went like this. So it got rotated by an angle theta. And if I take another vector y, which was like this, okay, that vector would also be rotated by an angle theta. And it's easy to see, therefore, that the inner product of these two would be preserved. Okay, the inner product here and the inner product here would match. Okay, the inner product matches under the diffeomorphism. Okay, so this rotation is actually an isometry. And the inner product also matches, okay, under parallel transport. Okay, by definition, the parallel transport should preserve the inner product. Okay, because that's what the unique metric compatible inner connection does. It preserves the inner product under parallel transport. Since all paths give you the same parallel transport, it doesn't matter which path I'm talking about to get from here to here. All paths will give me the same final vectors and therefore the same final inner product. Okay, but this again, you can see why this is special to the flat metric. Okay, if we were in a curved space, then there would be no unique comparison that we could make to some particularly parallelly transported version of this vector here. Okay, there is no unique comparison that can be made. And if there is no unique comparison that can be made, the only thing that we can say about this is that there is some diffeomorphism that has given us some new x prime and some new y prime, and the inner product of those is preserved under that diffeomorphism. Okay, then that diffeomorphism is in isometry. Okay, so let's look at an example of that. So let's look at S2. We look at a two sphere. Okay, and let's look at first diffeomorphisms on the two sphere. Okay, so diffeomorphisms of course can be anything, but if I look at isomorphisms, the isomorphisms are the ones which preserve the metric. Okay, and the isomorphisms of the two sphere can be understood from its embedding in 3 dimensions. Okay, they basically correspond to rotations of the two sphere in 3 dimensions. So I can rotate about the LZ direction, sorry, about the Z direction. So that is the LZ vector field, which looks like this. Okay, or I can rotate about the X, or I can rotate about the Y. This gives me a basis of killing vector fields. And this basis again is closed. Okay, so Lx, Ly is Lz and so on under cyclic permutations. Okay, so now under a flow, this point gets moved to this point. Okay, and if I look at a particular vector at this point, okay, and another vector here, so let's call this X and Y. Okay, the isomorphism is such that the pull forwards of these two vectors, the pull forward of these two vectors. Now, what does the pull forward of these two vectors look like? Okay, now in general, those are two tangent vectors at this point. Okay, the pull forward can be visualized by thinking about physically rotating this in 3 dimensions. And so I would actually imagine that I drag this along, okay, this integral curve. So the integral curve is something that goes along the flow. So I imagine that I drag this red vector along and I drag the purple vector along. Okay, I imagine that I physically have these arrows which are on a tangent and I rotate the entire tangent plane with the sphere. Okay, and so this would be rotated. So if I make a 2 pi rotation, okay, about the Z axis, then this red vector would come back to itself. Okay, under a 2 pi rotation, the red vector would come back to itself. Okay, so any vector under a 2 pi rotation would come back to itself under these diffeomorphisms. Or sorry, these isomorphisms. Okay, so if I make a 2 pi rotation by an isomorphism, okay, I would get back the same original vector. Okay, so these are isomorphisms. Okay, this is basically just a map from from the manifold S2 to itself. Now we are generating them by a series of continuous small diffeomorphisms. Okay, but you could think of one direct map from the initial configuration to the final configuration. Now what you can do is, instead of looking at this diffeomorphism and the pull forward of or the push forward of these vectors, you can instead look at parallel transport. Okay, so you can look at parallel transport. So what we will do is take this and let's imagine that you have again this vector field. Okay, this vector field generates this is a killing vector field. Okay, and this vector field generates an integral curve. Okay, this is the integral curve. And now let's imagine that you have some vector here. Okay, and we want to know what happens to this vector under parallel transport. Okay, what happens to this vector under parallel transport? So the way to visualize this, you can do it mathematically, but let's look at one way to visualize this. Okay, so what you want to do is you want to construct a tangent plane here, you want to construct a tangent plane here, you want to construct a tangent plane here. And you want to imagine parallelly transporting it from one tangent plane to the next tangent plane to the next tangent plane to the next tangent plane and so on. Okay, so the way to do that is you imagine this sphere and you now imagine, okay, let me draw tangents to each point, okay, on this latitude. Okay, so there's a latitude. You imagine drawing tangents to each point. Okay, so what this is going to give you, it's going to give you a cone. Okay, it's going to give you some kind of cone. And this cone is basically like, it's like joining all those tangent planes together. Okay, and this cone, now what I'm going to do is I'm going to open up the cone. Okay, so when we open up the cone, what it looks like is this. Okay, I have to glue these edges together and then I get a cone. Okay, so you can imagine folding it and then I'll get a cone. So this angle is called the conical deficit angle. Okay, it's not 360 degrees. Okay, and this basically is each point on the latitude. Okay, these are these points. And I can think of this as basically different tangent planes which are glued together. Okay, and now if I imagine parallel transport, okay, so imagine any kind of parallel transport. Let's say, let's imagine that, let's say we're going, let's take tangent vectors to this integral curve itself. Okay, so we can take these tangent vectors. So you would imagine that you're going something like this. Sorry. What do I want to argue? I want to argue that a tangent vector here, this is parallel transport. Okay, so this is what parallel transport looks like. But the point is that when I glue them together here, okay, so now if I glue this together and I ask what happens after taking some vector around the full latitude. Okay, if I imagine taking some vector around the full latitude, what would happen is that I am comparing this tangent vector with this tangent vector. And when I glue these together, okay, these tangent vectors are not pointing in the same direction. Okay. So when I glue it together like this, okay, this tangent vector will actually be rotated, okay, by an angle theta relative to this original tangent vector. I mean, can you visualize that? I have a video actually which I can show you. But it's on YouTube, and I want to upload these videos later. So maybe I mean I don't want a copyright conflict. So I'll just show you the video in a moment. Okay. So basically the point is that this tangent vector, when I glue it here, okay. Now the thing is, I have to look at. I mean, it looks like it's parallel because I've opened up this cone, but when I glue the cone together, you will see that this is no longer parallel to this. Okay. Yeah, I think the angle between them might be, yeah, so this angle is theta by 2. This angle is theta by 2. Okay, so when I glue them together, you will find that this vector and this vector differ from each other by an angle theta. Okay, so when at the point where I glue this cone together, which is here, this vector points theta by 2 this way, and this other vector points theta by 2 the other way. Okay, so the angle between these two vectors is theta. So what happened is when you took this vector around, okay, when you took this vector around the cone, when it comes back, it'll be at an angle theta to it, relative to itself. Okay, so in fact, even if I move a small amount, this vector is no longer parallel to itself. It picks up a small amount of angle as I go around. Okay, and then when I come back a full circle, it covers an angle theta, where theta is this conical deficit angle. Okay, it's the angle of this cone. And sorry, it's not this theta, but it's the angle when I open up the cone. Okay, this is the conical deficit angle. Okay, so that's the angle. This is the extra angle that I get. And so you see that compared to diffeomorphisms, okay, diffeomorphisms basically is just a rotation, and that rotation preserves this vector. Okay, so this vector basically gets preserved. That is actually the statement that since this vector field generates Lz, and I'm making a rotation by Lz, I'm taking the killing vector, that is, I'm taking the Lie derivative along Lz. And this is obviously 0 because this is just Lz. So there's no change in the killing vector field. However, here I'm parallelly transporting, but I'm not parallelly transporting. I'm parallelly transporting the tangent vectors to this curve. So I'm parallelly transporting the tangent vectors to this curve along this curve. Okay, but this is non-zero. Okay, and the reason it's non-zero is because a latitude is not a geodesic. Okay, a latitude is not a geodesic. It's only longitudes that are geodesic. So, for example, if I was actually going along a longitude, then this cone, you could see in the limit that if I start, lowering my latitude towards this, then this cone opens up. Okay, and my cone actually has to become like this if I want to subtend, if I want to have tangents here and here. So in that case, basically my cone goes to the limit where theta is equal to 0. There is no conical deficit angle. And therefore, when I make a full 2 pi rotation, okay, about the equator, okay, the tangent vectors come back to themselves. Okay, I mean, and they actually stay along themselves all the way. Okay, so in that case, basically geodesics or great circles. Okay, these are the only great circles are the only geodesics along a sphere. And but if I parallelly transport it along something that's not a geodesic, okay, like the scaling vector field associated with rotations, okay, along the z direction, then I would find that the tangent vectors change, okay, under this parallel transport, but they don't change under a Lie derivative. Yeah, and the other point is that when I want to compare this with something, okay, so let's say as I move from here to here, I want to compare this vector with something. Okay, I want to compare this with something. The thing is, I have no reference comparison. Okay, in the sense that, or when I say that I moved from here to here, I move from here to here, and if I want to and so we say that we are rotated by an angle theta. Okay, we are rotated by an angle theta relative to the vector field that was originally over here. Okay, that is, we're rotated with respect to the k that was originally over here. But this k itself, okay, when I parallelly transported, this has moved forward and this is also rotated by an angle theta. Okay, so of course, if I'm only talking about one vector, then I'm rotating this. I parallelly transported this, and now I got this. Yeah, sorry, to draw the contrast with flat space, right? So supposing I want to say, with parallel transport, can I compare this with a particular unique vector here and say that this is the parallel version of this vector at this point? And the answer is you can't, okay? Because there are many paths that I can take to get from this point P to this point P prime, okay? And to get from this point P to P prime, I could follow a geodesic. Okay, the geodesic would look like some kind of great circle, but I don't have to follow a geodesic. Okay, I could have followed, let's say, I could have chosen some arbitrary north pole, and this could have become a latitude which connects them. Okay, or this could have been some other curve. And we've seen that in general for arbitrary curves, for example, for latitudes, the vectors rotate. Okay, or the vectors change directions as I move from A to B. Okay, so there's no unique notion of what it means for a vector at one point to be parallel to a vector at another point, okay, on a sphere, because the sphere is curved. Okay, so there's no unique notion of parallel, comparing vectors. It's path dependent. Okay, what I call parallel here and parallel here is path dependent. Okay, whereas in R2, there is no, I mean, that notion becomes path independent, but that's not true for a general curve manifold. Okay, let me just show you this quick video. I'll just stop the recording.